And thanks Michael, Martin, Susan, and Mohammed for organizing this wonderful event. And thanks for inviting the experimentalists. Much appreciated. I would like to firstly acknowledge all my funding agencies that have allowed us to do this work. And I'm going to talk about exciton-photon coupling. And the reason I have this title, Beyond Anti-Crossing, is because in the experimental community, it's become fashionable to show strong coupling, where you just show two peaks. And and as June pointed out this morning, you can actually run a transfer matrix simulation and show those two peaks. So there's, so I want to see what is the manifestation of strong coupling, and if there are some effects that one can see. So the field of exciton polaritons is quite old, starting with the early work in 1992 with Claude Weich's book showing the formation of strong coupling. It's really started this field of exciton polaritons, and a whole slew of phenomena that have been observed, and a whole class of material systems that have been studied. And I just highlighted a few different things ranging from, emulating Dirac cones and so on to even realizing XY Hamiltonians and so on with these polariton condensates. For the purpose of today's talk, I'll focus on van der Waals materials, and this is a cartoon taken from Dimitri's well-known perspective article, and I'll focus only on exciton polaritons, but not just on these transition metal dichalcosanides, but some other materials as well. So this is some prior work from my group where we started with some strong coupling experiments and went on to show some interesting physics. Here is one example where the gradient of the field that gets generated inside these cavities actually played a role in breaking the symmetry requirement for second harmonic generation. So strong coupling does bring something to the table. But what I want to talk today about, I have two parts. The first part is on exciton polaritons in van der Waals magnet. And the second one is on how to enhance polariton-polariton interaction so that I can get correlations in the photons. So towards that, we haven't gotten there yet. So the first part on van der Waals magnet, I want to introduce you to a van der Waals magnet called chromium sulfur bromide. It's a van der Waals semiconductor. It's a square lattice as shown here. When you exfoliate it, it's highly anisotropic, so you get these long strips as shown here. And it is a semiconductor with a band gap of about 1.5 eV, Néel temperature of 130 Kelvin. Each layer is a ferromagnet, and the adjacent layer is also a ferromagnet, except the spins are pointing in the opposite directions. So it forms an AFM state, and it's also air stable. When you apply a magnetic field, you can, of course, align the spins, and the result of the spins is that now your exciton, which was sitting in one of the layers, starts hybridizing with two layers, and you get this, and the result of that is if you probe the exciton energy as a function of magnetic field, you see a reduction in the energy of the magnetic exciton, and that is because now your exciton localization has got modified because of this alignment of the spins. And this is along the C axis, which is perpendicular to the layers. B is parallel to the layers, it's the EZ axis, and you can see you can flip the spins with less than 0.5 Tesla magnetic field. Now what is really fascinating about this material is, although it's a 2D material, it's really a quasi 1D material, in the sense that you're forming these narrow stripes along the B axis, and the refractive index or the dielectric constant along the B axis is extremely large. As you can see here, the dielectric constants, these are extracted from the experimental reflectivity data. Along the A axis, it is kind of like the regular semiconductor, and same along the C axis. So it's only along the B axis that you have this large dielectric constant, and in fact, Dmitry Basov's group demonstrated that in fact it does form a hyperbolic medium because the dielectric constant actually goes negative in this spectral range. So it's also in the visible, but it's over a smaller spectral range compared to the moly oxide chloride that you heard about earlier from Dmitry. But the result of this is that if you go back to the old paper from Hopfield, it says clearly here that when you have a large dielectric constant, the eigenstates of the system of crystalline radiation field are mixtures of photons and excitons. Or in other words, just because the dielectric constant is so large, the excitons are already dressed by photons inside this material. So you don't have excitons in a bulk limit here, you only have exciton polaritons. And in fact, you can see that right away. If you take a bulk material and you look at its photoluminescence, you will see not just emission at the exciton or around the exciton resonance, but you will see a whole bunch of other peaks, all of which show a dispersion, and the slope of the dispersion changes as you go farther and farther away from the exciton. So these are all polariton branches which are formed naturally inside this material. And so this was a collaboration between the groups of Andrealu, Sofer Zednik's group, who grew the materials, Chardin's group, with whom we did some of the time resolved measurements, and Francisco and Akash, who helped us with some of the theory. And these are the key players here. Florian, who is now going to start a new independent program at TU Munich. So this is what happens in a bulk material. You can get the polaritons, as you can see here. But if you put mirrors on top, then you just improve the Q of the cavity, and you get better mirrors. And of course, you can also get strong coupling with just few layers of this material. And what we showed back in 2023 was that if you take these polariton branches and if you probe them, if you come with a pump pulse, what happens is you excite the magnons. You have a finite magnetic field acting this way, so you generate the magnons, and the spin waves start processing, and you can read this out through the probe. So there was a work prior to ours from the group of Xiaoyan Zhu at Columbia, who showed that the excitons inherit these magnon oscillations. So what we tried to show here was, do the polaritons, the exciton polaritons, which are far removed from where the excitons are sitting, also demonstrate this? And that was actually shown in this paper here. You can see the oscillations that are superimposed on top of these exciton transients. And in fact, if you take a Fourier transform, you see that the frequency indeed corresponds to the magnon frequency in this material. So this is old work, so 2 years, almost 2 years. But then we started looking at this material a little bit more in detail. And what we saw was that this is the exciton that we were probing. And you can see here, the exciton has a very narrow line width, and it's got these resonances. But then if you go to higher energies, you start seeing another feature here. And this was a little, we were not sure what this was initially, because the initial works all reported band gaps of around 1.5 eV. So what is this feature we are seeing around 1.7 eV? Well, nevertheless, we went ahead and looked at its magnetic field dependence. And to our surprise, what we saw was, this is the magnetic field dependence of the A exciton, or the exciton that is at the lower energy, exciton that we were all studying. But this is the magnetic field dependence of this higher energy exciton. So you get an over 80 milli-electron volt shift with the same magnetic field in this for this higher energy exciton, clearly telling us that these excitons are much more strongly correlated to the magnetic order. So not just in steady state, but you can also do a time resolved experiment. So this is a trace of the magnon oscillations of the low energy exciton at 0.4 Tesla. So you can see the amplitude of oscillations. For the exact same power levels and all the exact same conditions, you will see that the magnon oscillations are much more for the higher energy excitons. So clearly showing that the exciton magnon coupling is stronger for this higher energy excitons. So we collaborated with a group of from NREL. Swagata led this work, and he carried out these calculations, which showed that the lower energy exciton, the 900 nanometer exciton, is actually much more localized, and it's very Frankel-like, whereas the higher energy exciton is more Wannier-like. And then when you go from the AFM state to the FM state, it indeed does hybridize with the adjacent layers. So this explains why this is probably more sensitive to the magnetic field compared to the lower energy exciton. So but what struck us was the following. So since we have these excitons and polaritons inside the system, we were interested in understanding what is the nonlinear response. So the experiment is as follows. You come with a you come with a pump pulse, a narrowband pump pulse around the polariton or the exciton energy, and you probe what is the reflection of it as a function of pump fluence. So what we saw was that at zero magnetic field, so zero magnetic field is shown here, as I increase the pump fluence, the fluence dependent shift is very small, barely noticeable. But then as we started changing the magnetic field of this in the system, we started seeing that this nonlinear shift suddenly started increasing, and in fact it got to a highest value of around 1.5 Tesla. And then we sweep it back, and then it goes back to at 2.5 Tesla. When the system has gone back to the ferromagnetic state, it is completely cancelled out. So clearly telling us that you need canted spins for these interactions to happen between the excitons. Or in other words, magnons are playing a role in the exciton-exciton interaction here. So if you think about exciton-exciton interaction, typically we think about exchange or phase-space filling type effects. But here we are seeing that the magnetic field is playing a role, and it clearly comes from the contribution of the magnons at some finite magnetic field. Now we have, and just to prove that in the case of the lower energy exciton, the one that was at 900 nanometers, we don't see much of a shift in energy. It is within our error bar, so we can't claim anything. So it's only the one that is more strongly correlated to the magnetic order that shows this effect. So we have a kind of a cartoonish picture of what might be happening here. So this is magnetic field here, and this is fluence. And so we think as we increase the exciton density, the increase in exciton density starts playing a role in an additional parameter beta, which changes the angle between the spins of the two adjacent layers. So these are the yellow and the pink are the two adjacent layer spins, and this beta factor comes in as I increase the fluence. We're doing more experiments now to look at the frequency of the magnon as a function of fluence, where we should see this effect also showing up. But nevertheless, this is the picture that we have of why we might be seeing this magnon-dependent exciton-exciton interaction here. So if I in fact plot the nonlinear shift, so first thing I want to point out is unlike exchange interaction, which is repulsive, that we normally see a blue shift, here we see an attractive interaction. So the energy redshifts. Of course, when you see a redshift, the first thing that comes to your mind is, haha, it might be heating. But we have actually tested this with different rep rates of the laser, going to extremely low rep rates where there is no heating effects, and we still see this. And also, we don't see this effect for the higher energy, for the lower energy exciton. So we have removed the heating effect. Yes, Mohammed.
Taking back a little bit.
Yes. Yeah.
You had a plot that you showed the dependence of the excitons with respect to the magnetic field, and then one of them was insensitive. So what was the take home?
This one?
Yeah.
Yeah.
So what did you learn about the nature of the exciton? Because now here it's linear, right?
So this one,
and also like the dependence on the magnetic field is quadratic. It's not that.
Yes, this is the magnetic field. So this one is along the a-axis. This is along the c-axis. This is along the a-axis, and this is along the b-axis. So b-axis is the easy axis where you just get a flip.
Okay.
A and these ones show the typical dependence that you see.
So how should I think about this exciton now? So when you so excitons and the magnons are coupled, right?
Yes.
That's your picture.
Yes.
Right? How do I now understand what's the mechanism? Is it like coupled to a single magnon or a pair of magnons? So before the nonlinear part, what?
The nonlinear part.
You know
the nonlinear part, we have taken it as a single magnon.
That
picture.
Each exciton will,
yes.
When I create an exciton, it also
creates a magnon because you're using a pump pulse in the experiments. So this is at a finite magnetic field, right? So you need we are reading it out, reading the magnons out through the excitons.
So I assume as a function of magnetic field, your magnon spectrum changes.
Yes, of course it changes in frequency.
Very good.
Yes.
So is it possible to use that use the linear data?
Yes.
To understand how this exciton is coupled to the magnon, or no? It's a little bit black magic so far.
How the well, I think the exact details of the exciton-magnon coupling is still unclear.
Yes.
Yeah. So that's why we have used this cartoonish picture to just say that, okay, when I increase the density, there is something that is influencing the angle between the spins in the adjacent layers. Mm-hmm. There's a density-dependent term density dependence that's coming in for the excitons.
I think.
Yes.
Following Mohammed.
Yeah.
Why you rule out magnon-phonon interaction?
Why I allowed?
Or you rule out?
Rule out?
Because
so
the
no.
phonons will create two magnons and will couple to the excitons, because exciton-photon is very strong in this material.
Good question. So, in fact, if you look at our data here, this splitting, which is about 1 gigahertz, corresponds to probably the splitting that you see when an acoustic phonon and a magnon mode couples. So there is that. I cannot ignore that. But are you asking this in the context of the nonlinearity? But then we should have seen that effect also for the other exciton. The phonon effect is there in the other exciton as well, if it is a heating effect, right?
A question along
Yes.
the same lines.
Yeah.
So should we think about it as a matter of localization of the wave function, in the sense that
Yes.
if in this intermediate regime the wave function is more delocalized and therefore the nonlinearities?
Yes, but the wave function in the ferromagnetic state is also delocalized, right? So it actually gets an interlayer hybridization when it becomes fully ferromagnetic. That's why the energy is shifting to lower energy as I increase the magnetic field. So it's just not that, right? Because the wave function does, but there is also the fact that I need some intermediate magnetic field where the spins are canted for this higher nonlinear response to be observed.
So the maximum redshift you get is the same as what you get with at 2 Tesla with magnetic field, right? That should saturate.
This one, right?
No, this, yeah, so this is the, what, 80 milliamps?
Yes, yeah.
So when you increase the power, this is...
so when I increase the power, what we see is, if you look here, at very high, so this is done at, 2.5 Tesla, right? And then this is done at, you see that very high fluence, it starts saturating out here.
So actually, I mean, if you were doing resonant excitation, I would agree with you that this would describe essentially in magnon-mediated interaction. But the system is not necessarily have unity efficiency. So if you do off-resonant excitation, you generate large density of magnons. And that
maybe I can explain this experiment. Yeah. So the way we do this experiment is you have the magnon, this dip here, right? Yeah. We go with the white light supercontinuum, which is resonant around here, just around here.
So you do
we're doing resonant. Sorry, I'm my bad. Yeah, we're doing resonant pump, exactly. Yeah, we've taken lessons from you. Any other questions? Yeah, so this is a resonant pump experiment. So anyway, so this is what we see, and we see that the largest shift we are getting is at some finite magnetic field when we have this, when we do look at the nonlinear shift. This work was done in collaboration with Akash and Swagata at NREL, and these are the guys who really did this work. Pratap and Sichao and Bishwajit and Agneya did the magnon dynamics from Matt's group. This work should be coming out soon. But now, we went on to ask the question, do these oscillations exist for polaritons as well? And this is where the excitons are sitting. And here, in this particular experiment, we are pumping at 600 nanometers. And you see that the magnon oscillations exist every time I'm seeing a phase shift. It corresponds to some resonance in the system. And I see that the magnon oscillations are there for all the polariton branches that exist between here and even at 1000 nanometers. So in fact, I've taken a trace here, and you can see here the magnon oscillations are visible, not just for the excitons, but also for all the polariton branches, even going down to close to 1000 nanometers. One other point, it's not there in this data, is that I can pump the system even here, and I can still see the magnon oscillations out here. So I can drive a polariton, and I can still see the magnon oscillations happening at higher energy. So it's still a very interesting material system. I think there's a lot of things to be discovered and understood. Happy to take any more questions on this. If not, I'll switch to another related topic. Yes, Anhal.
I think what you are saying is that the exciton in this material is the driving force of the magnon generation.
I'm not saying the exciton is the driving force of because I just told that I can pump at a frequency that is even lower than the exciton. like all the way out at 1000 nanometers, I can do a pump, and I can still see oscillations. Excitons are just used to read out the...
Yeah, but then if you don't read out, if you don't have the exciton...
No, I can pump here.
Much
I
higher.
can come to the white light, and I can still see it.
Yes. Then I think you're saying that basically it's the exciton that is coupled and is doing this launch of the Magnum modes.
I'm not still sure about it. Yeah.
Exciton character of the
Polariton, yes, that I agree, yes. But I don't know, I can't say with certainty that the exciton is actually launching the magnons. That I don't have any evidence for that to say it with complete confidence. Yes.
Sorry, maybe I missed it actually. What temperature was this at?
This is all 4 Kelvin experiments.
So, but there's this mystery magnetic phase, right, in the system at 4?
No, that is in, you're talking about where you go from AFM to FM?
No, there's this like second, possibly defect magnetic phase, right? There's a second transition, right?
So that's around 1/3. It's around the Neal temperature, if I'm not mistaken. That thing. I don't think it's at 4 Kelvin.
It was between 4 Kelvin and the Neal temperature, I think.
Okay, but this is all done at 4.
But
in fact, the last
also,
ones are done at 1.7. Actually, the magnetic field experiments are done at 1.7 Kelvin.
It was this possibly like polaronic magnetism, so basically defects magnetizing, right?
Is this the Klein paper?
Yeah.
Okay. Yeah, but those ones had a very different magnetic field dependence. I was on. Yeah, those had a different magnetic field dependence completely. Those defect states. They barely moved.
Yeah, exactly.
With magnetic field, but here we see much larger shift.
But those were thought to be magnetization mediated by conduction or sort of dilute carriers. So if you populate an exciton into that, it could perturb the secondary magnetic order, right?
Possibly. Yeah.
Okay.
We can talk. Yeah.
Out of curiosity, like, how do you know if the interaction is fully coherent? Like, do you see any change in the line width as you increase the fluence?
Yes, the fluence gets. So we have also done fluence dependent. These experiments in fluence dependence, and what we see is that the system decays faster. So the coherence time decreases. But we have to still analyze the data. But what we see is that this decay time is shorter when I increase the fluence.
Like, is there a sense of how does that compare with the energy shift that you see in the, or?
No, I don't have a number for that. Yeah.
So to see that whether there are only virtual magnons,
yes,
mediated directional field magnons, you could do
distance,
right?
Yeah. So we are just doing those attached. So we are pumping here and probing where the real
I meant in time.
In time.
Generate at t equals 0 and then see if you come in, say, 100 picoseconds.
Yeah. So now that we finished these, we just start getting ready to do those. Yeah. Joe Orenstein has a paper where he has looked at the magnon propagation. They've done a time dependent experiment, but they never looked at the nonlinear part of it. Yeah. All right. How am I doing? Okay. So second part of the talk, we're going to talk about another effect of polaritons or strong exciton-photon coupling to increase polariton-polariton interaction, and the motivation there is, can we get photon correlations? And of course, so the idea of polariton blockade or photon blockade is the idea that you come with one photon, you create a polariton, and the second photon comes in and it generates a nonlinear interaction such that the second photon, there's enough energy shift that the second photon doesn't get absorbed, or it actually knows the fact that there was already a polariton. And actually the seminal work in this just a few years ago from the group of Mamaglu and also from Thomas Waals, and more recently a paper that's on the archive from Ronan Rappaport's group, where they've all studied this effect where initial evidence of correlations of the photons have been observed. So it's very exciting because we work with 2D materials, and then so in a so if you think about polariton interaction, there are two contributions. One is the exchange interaction, and the other one is the I have no idea what's going on here. And the second one is the phase space filling effect that is shown here. So now, if I take this second effect, that is usually seen as a reduction in the Rabi splitting, and the first one is seen as a blue shift of my exciton. And now, there has been a lot of prior work in this idea of using dipolar polaritons as a way to increase the nonlinearity. And the idea here is that you have a quantum well that is in one quantum well and the second quantum well, and then you hybridize the interlayer exciton with the intralayer exciton, as shown here, and this results in enough sufficient oscillator strength, and you have a static dipole moment, so you get larger interaction. So these are two early works, again, one from the group of Imamoglu and the other one from Ronan Rappaport's group, where they've reported, this work reported extremely large nonlinearities from these interlayer excitons. Now it turns out that bilayer moly disulfide naturally forms interlayer excitons that are hybridized with the intralayer excitons. And this is something that was reported in 2020 here, and you can see there that because of this hybridization between the interlayer and the intralayer exciton, you get a sufficient oscillator strength. It's about 30% of that of the intralayer exciton. Also, because it has got a permanent dipole moment, you can actually, static dipole moment, you can actually apply an electric field, and you can see them splitting in the degeneracy. So the degeneracy comes from one being up, down, and the other one being down, up. And so you have the two interlayer excitons. Now the current understanding of these excitons is that the hole is delocalized between the two layers, whereas the electron or tunnels between the two layers, and the electron sits in one of the layer, and these are the two static dipoles in this system. Now, so this is the differential reflection. This is the typical A exciton that everyone studies. This is the interlayer exciton. You can see it is pretty dominant. And if I look at the exciton density dependent blue shift, you will see that it is the blue shift of the interlayer exciton is greater than that of the A exciton, showing that the dipolar interaction does play a role here. So we made a cavity, which is basically a DBR mirror with this bilayer MOS2 and just a silver mirror on top, so the Q is not very high. But what we see again is that the cavity mode strongly hybridizes with the A exciton and the interlayer exciton. And then once again we go and do this resonant experiment where we either pump just this polariton branch or or in this case we pump around the Rabi splitting of the interlayer exciton. And what we see is the shift that is happening for the interlayer exciton and the intralayer exciton. And what we see is that the interlayer exciton shows an interaction strength which is about 10 times that of the A exciton. Now, the numbers might have mistakes because there is estimating the polariton density is key to get these numbers right. However, the scaling between these two, which is about a factor of 10, seems to be reasonable. And in fact, we were able to establish by looking at the Hopfield coefficient that at low polariton densities, the dipolar interaction actually starts playing a key role in this nonlinear interaction that we are seeing. So just to summarize, what we saw here is that you need about 100 photons to shift by one line width, and the enhancement is about 10 times that of the intralayer excitons that you see. So the permanent dipole, the static dipole moments that you have in these materials do play a role in the nonlinear interaction that we are seeing. I must point out, however, here we have not applied a field. So in this case, you have, in an ideal situation, you would have equal number of up and equal number of down. But we know that in a cavity with different stacking and different materials on top and bottom, we have broken the symmetry. So all we are seeing is an effect of residual dipoles that are there in the system, and even with that we are seeing a reasonably good interaction. We are currently working on devices with an electric field where for the excitons we already see a larger nonlinear shift. I must point out this paper that just came out last year, Ataj is also on this paper, where they've estimated the enhancement from the dipolar interactions, and they estimate a number like 5, and we get a number like 10, so which is within the same order of magnitude. It's not the huge numbers that were predicted in one of the other papers, but I think it's encouraging that we can get these effects. But it's equally important to point out this particular line in this, say that leads to a drastic enhancement of polariton interactions as compared to bare excitons. So usually you would think that when you go to polaritons, the interactions should go down because there is a photon component in there and the excitons are, excitonic component is lesser. However, this calculation shows that that's not the case. Actually, in the polariton picture, you get a larger interaction. So I highly recommend you to look at this paper to get a better idea of what's going on here. So of course, our goal is now to take these systems and put them inside cavities. But another system that everyone is excited about is if you can create a Moire excitons, because they have also been shown to have large nonlinearities. However, if you, from Ajit's talk this morning, you saw that to create these Moire excitons, you need the interlayer excitons to be formed. But typically those interlayer excitons have very weak oscillator strength. And so what we have done is we have taken a different platform. We have taken twisted boron nitride, and what twisted boron nitride does is it creates these ferroelectric domains A, B, and BA, as you can see here, and this is the AA domain where the atoms are sitting bang on top of each other. And this is a Kelvin probe force microscope image showing these domains that are formed. Now it turns out that if I look at, so of course you can change the Moire lattice and all of that with the twist angle, but if I place something on top of these twisted HBN layer, you get a potential that the excitons on the top can feel because of the twisted boron nitride. So this is the idea. You take twisted boron nitride, which creates this ferroelectric domains, and then you place your target material, which is in this our case molydiselenide, on top of this, and you get this nice potential that the excitons in this MOSC2 will feel. Now, this is the KPFM image of the twisted boron nitride, and this is the KPFM image of the molydiselenide on top of the twisted boron nitride. And you can see here from the line cuts that they have roughly the same potential, except the one on MOSC2 is more noisy. So, so these are the as twisted structure, but we also came up with a technique to make larger domains. So it turns out that you twist once, and from that substrate you pick it up and you put it on the second substrate. There is lattice reconstruction, giving rise to much larger domains. As you can see here, this is 2 microns. So now this allows us to do far field measurements of these materials. So we have gone ahead and looked at what happens in this. So this is a cartoon showing what might be happening. So depending on whether we are in the BA or the AB domain, you can have excess charges that are on this side versus on the AB side, which means you start forming Fermi polarons, the repulsive and the attractive polarons, and depending on where you are, you should be seeing this kind of a shift in the exciton energy as you go towards the different regions. So that's in fact what we see. We go from the BA to the AB domain, and we see that in the BA domain, you're dominated by very exciton-like emission, and then you go to the AB domain, and you start seeing the emergence of this trion or the attractive polaron peak showing up here. In fact, if you can trace this as a function of position, you will see this shift that is happening as was expected. So there I must point out there are, I think I had it in my first slide, there are 3 other related works from 2 of the, from Atacha's group and also from Yu Zhu's group. They've done very similar work and seen other interesting physics from the same platform of twisted boron nitride and proximatizing a Moire lattice on TMDCs. So we see the same effect on Rydberg states, and as a function of twist angle, you can see what is happening to the A exciton and to the 1s state and the 1s minus state, and you can see here the dependence on the Moire size. And this is work led by Kwang Hee and Min Hyun, who are visiting students from the group of Yang Dek Kim. And the last thing we want to do is, of course, make this into a cavity and then look at the cavity effect in these systems. So with that, I'll summarize, and this is the 3 results that I talked about today. And of course, all of this work was made possible by all these wonderful folks. Thank you.
Ajit, maybe you start.
Very nice talk, Vinod. One question about you showed that even for zero magnetic field with power, you saw redshift, right?
Yes.
If you
well, very small redshift. I mean, it's within the error bar.
Right.
Yeah.
So if you were to convert that into an effective B field, how much would that be? Because you see that some kind of a redshift with the. So assuming that you have low power and you apply some B field to get the same amount of redshift, how much would that B field be?
We have not. I don't know the quickest idea.
I see. Because what you showed was a very sharp.
Yeah, for the 1.5 Tesla field.
Right.
Yes.
And so there it was directly going to 80 milli shift.
Oh, 40, yeah, something like, yeah.
Okay, thanks.
Hi. I'm wondering regarding the last slides you had with the domains in the HBN. So one of the things you can do is apply an out-of-plane field in order which actually changes the local reconstruction and changes the location of the domain walls. Do you have any thoughts on how that would impact?
Yeah, so what we've just done some experiments where we see that these domains can be made larger and smaller by applying the thing, but yeah, we haven't done extensive PL experiments on those ones. No. Yeah, absolutely.
Yes, here.
Yeah.
Wait. Sorry, you have to wait for the. Thank you.
Thank you for the nice talk. I have a quick question about the shift which you show in the first part. So is that shift coming from exciton-exciton interaction or from exciton-magnon interaction?
Exciton-exciton interaction.
Is that from A exciton and B exciton interaction or B exciton and B exciton interaction?
So we don't call it A and B. The high energy and the low energy.
Okay,
exciton,
is it from high and high?
It's
or
the high energy exciton. So the low energy exciton does not show a shift, or it's within the error bar of the experiment.
Sorry, I guess. So you think this shift is coming from interaction between high and high energy excitons?
Yes. Because it's a resonant experiment I'm doing. I'm just pumping just at the resonance of that second higher energy exciton.
Yeah, but typically the high energy exciton would relax to the low energy exciton in a very short time. And from your PL measurement, the PL of the high energy exciton is pretty weak. It's 3 times weaker than the low energy exciton, and also the strength is similar from your absorption.
Yeah, but I still see the dip, right? When the dip, all of this data is where I can resolve a dip of the exciton.
Yeah, I mean, the oscillator strength is not small, but the PL is weak. So that means the lifetime.
The PL is extremely weak.
Yeah, exactly. That means the relaxation is very fast. So basically, you won't have a high density of high energy exciton. So all of them will relax into low energy exciton within a short time. I mean, at least from your data, that seems to be the case. Okay. So I'm wondering, yeah, maybe this is coming from interaction between high and low energy exciton, or maybe from high energy exciton and magnons.
Can't see how this would come from high and low energy excitons, but
okay. I guess this is a different possibility, but I guess the main question I had is because the high energy exciton typically will have very short lifetime, so you won't have a high density. Even if you pump it very strongly, they will relax into low energy excitons in a very short time, or some low energy excitations. So it's a bit surprising that if you think this.
But I'm seeing an energy shift, right?
Yeah, but this energy shift can be coming from interaction with the exciton and many other things. Not between high and high energy exciton. It's just the high energy.
But I have time resolved data also, right?
Sorry?
We have time resolved data that shows the exciton is existing during the time we are doing these experiments.
Yeah, man, that is fine. Yeah, your data basically that's coming from magnon, right? You see coherent oscillation, which is from magnon. So that's also the reason.
No, but we also have extracted the time trace. You can remove the magnon oscillations. You can see the time trace, right?
I guess we can probably discuss later.
Yeah, thanks. That would be good. Yeah, thank you. Maybe.
Can I ask?
Yes.
Okay. I would just like to get an intuition. You want to somehow optimize exciton strong interaction, right?
Yes.
Can you tell us what is your intuition? What should be material properties, particularly band structure, excitonic radius, or so on, which would optimize this, which is optimizing this?
Okay, so good question. So we first started approaching the problem with, so of course dipolar excitons are good, because they have a static dipole moment and there is interactions between them. So that's, of course, one approach to do this. We also approach the problem from Rydberg states, where you have larger Rydberg states in the excitons. And cuprous oxide, for example, has very large states. in TMDs, what we found was I can go to 2s or 3s states, but the oscillator strength drops so drastically that I can't really use it for cavity coupling. So to give you an answer for what would be a, I'm putting my bet on dipolar excitons or some correlated excitons that come, correlations that come from, you know, these Wigner crystal type things which are proximatized. But other than that, I don't.
What about this first one where you have also now strong magnon interaction? Is this?
Yeah, so the problem there again is the line width is so big, right? So that's our problem. So you can get a large interaction strength, but you still have a large line width. And this is the same problem with the dipolar excitons in MOS2, bilayer MOS2. Yeah.
Thank you for the nice talk. So you show that the magnetic field response of the exciton is highly anisotropic. So I was wondering, I'm not familiar with the selection rules in the material. If you can shine like perhaps different linear polarization, maybe out of plane or in plane.
So in this material, the PL is linearly polarized, and that is actually not coming from the spin orientation. It's actually coming from the anisotropy of the crystal. That's what we understand.
Yeah. Yeah, I'm curious if you can selectively maybe excite some magnons with a certain circular polarization.
We've not tried it. Yeah, we've not tried it.
Thank you.
Yeah.
My question was kind of related to the previous one. These magnons, this is a band of magnon, right?
Yeah.
But you said that it's broad, but it's still interesting that it's narrow. You still see a resonance.
Oh, you mean?
Because naively I would have thought that it's a bath. That's like a band of magnon that you create.
No, but the data that I showed is at 1.36 eV, right?
Uh-huh. Oh, okay.
Right? That dip I'm showing is at 1.36 eV. Okay. The two bands I showed is a Fourier transform of the oscillations that I saw.
So what was the width?
That width was, boy, I'll have to go back. See if I can get it to. No, not this. Here, this one here. But we are only looking at close to Q equal to 0 probably.
I see.
Right?
That's why. Okay, so momentum basically fixes that.
Exactly.
Q0 and then maybe it's just single, not pair. That's why. If it was a pair, then it would have been crazy. Yeah.
And then? Take your another one. Vinon, going back to the last part. Molybdenum
selenide on top.
On top of the HBN, and you have these ferroelectric domains.
Yeah.
Have you thought of having doped molybdenum disulfide in which you have the electrons and use this difference of excitons in the two ferroelectric and give the pairing between the electrons?
I think Attach has already got a paper. So this paper here, I think, this paper here talks about where they put excess carriers.
Then, because that one was one of the reasons, and then do you see corrugations of the top TMD? Because you know that all those systems, when you put one on top of the other, and they are not homonuclear.
No, so the topography is pretty good. The potential that we see when we do KPFM, we see this, but the topography is pretty flat. We actually do cleaning. The AFM cleaning, we do that also. So it's pretty,
Interesting.
Just one question concerning the polariton blockade. I mean, there always this curse of the line width being broader than the repulsion.
Yeah.
Now, in your case, the line width is limited by disorder, or you have the radiative line width, which also comes in?
So in the dipolar exciton, I think it is the, the material that we have is MOS2 that is reasonable and it's encapsulated in HPN. Mm-hmm. We've gone down to low temperature. We can't seem to get anything lower than what we have right now. Mm-hmm. Mm-hmm. So, maybe a higher Q cavity can buy us something, but it won't buy us much more. Yeah.
Okay. Well, there's maybe the last question back there.
In the first part, you said that increasing the fluence and seeing the shift is the witness for an interaction between the excitons. Is it in this
class of materials possible to quantitatively translate fluences to doped charge carriers, or?
Oh, you mean photodoping?
Yeah.
So we've thought about photodoping as a result of this, but photodoping should have also influenced the other excitons, and we don't see the effect on that one. And also the magnetic field dependence. How do we explain the fact that you need this intermediate magnetic field to get this shift, right? Photodoping should have happened.
Okay. Well, if there are no more questions, thanks Vinon again. And let's thank all the speakers and